First of all, I would like to thank the organizers for organizing such interesting weeks on differential geometry. And it's an honor for me to present my work here at this wonderful workshop. My presentation will be about geometric learning via PDE-based group equivariant convolutional neural networks. And what I will show in my presentation is that essentially what we do in a PDE-based group convolutional neural network is that we train the so-called association fields from neurogeometry. This is joint work with people in my group. I'm the PI of the group, and I lead the group on differential geometry and geometric learning. Group members include here Assistant Professor Bart Smets, PhD students Gijs Bellaert, Nicky van den Berg, André Companets, Vin Sherry, and Leander Vis. And also would like to mention some collaborators from other universities, Gautam Pai, Erik Bekkers, Jean-Marie Mirabeau, Mireille Boutin, Barbara Tumpach, and Ian Porteous. Okay, so I will start off with a motivation that comes from medical image processing. Nowadays, I'm also much working on industrial image processing. But yeah, to make this theory or the framework of PDE-based group convolutional networks was inspired by medical imaging applications. So I'll start off with a little bit of motivation from that applied field. In medical image processing, one encounters a wide variety of medical image problems where you have to automatically segment and track elongated structures, such as blood vessels and fibers in diffusion MRI. And yeah, of course, with medical imaging, you want to spare the patient, then you reduce the amount of radiation dose. And then these images are noisy, and it gets more complicated to extract these elongated structures and also to follow them, to track them. And yeah, on top of this, these elongated structures, they typically exhibit crossings and bifurcations, and that is a notorious problem for existing segmentation and tracking algorithms. So we want to find a generic solution to this. The problem is that often automatic algorithms in industry, and they don't work at these complex structures. They take the wrong exit. And then it's very costly in the clinic for the end user to correct these mistakes. And we want to deal with that problem generically. I'll illustrate the idea on a very specific example. This is a 2D X-ray image of a coronary artery. And then in the clinic, the doctor, he clicks at the yellow dot. And then he's navigating his catheter, clicks at the yellow dot, and then the industrial tracker takes the wrong exit as indicated in the red circle. Yeah, this is just one instance of whether this goes wrong. You take the wrong exit at the complex structure. I mean, we need a generic solution to that. We will need a multi-orientation approach, as I will show, and we need to not only do in this multi-orientation representations of images, geometric tracking along geodesics, Riemannian or Riemannian geodesics, and then project it back on the image space, but we also have to automate that process, because these Riemannian and sub-Riemannian tracking methods, they involve coefficients of the left invariant metric. And these coefficients have to be constant because of left invariance, and these will be the weights of my network. So this is the solution via PDE-based geometric learning. And here I have a philosophy. On the one hand, you have an image processing, advanced geometric image processing techniques. And then there is deep learning. Well, if you merge the two, then you have the two goods of two worlds, because with geometric image processing, we at least have a very clear understanding of what we're doing. We have geometrical models, we have PDEs, we have geodesics, we have nice models that describe, hey, these indeed are the optimal paths. And on the other hand, yeah, these geometrical models, they involve some parameters, and we would like to automate that, and deep learning is great in automating that. On the other hand, the neural networks, they are just designed with convolution kernels, meaningless convolution kernels, even for the equivariant group convolutional networks. The kernels have very little meaning, just sampled on some grid. There's no real geometric descriptors, and it doesn't give us insight in what the neural network is actually training and learning. And I would like to change that. I want to use the PDEs to understand, to do redesign the networks, so we do new implementations of neural networks, PDE-based group convolutional networks, so that we can interpret the results, the network flows, and on the other hand, the previous methods of geometric tracking that we do in the lifted space of positions and orientations to deal with all the crossings and bifurcations, they need to be automated. We're going to merge these two worlds. A key aspect of my approach, both in the geometric segmentation and tracking and in the deep learning, is that in the first step, I'm going to lift the image to the space of positions and orientations. And this is intuitively visualized over here. And then we're not going to do the geometric tracking or find the geodesics in the image domain. We're going to do that in the lifted space of positions and orientations. And the lifting is typically done. You have an image F from R to R. You probe that image F by a family of group coherent wavelets. Then you get a new function on the group, which is a multi-orientation representation of the image. And this is what we call the orientation score of the image. And in that orientation score of the image, which is, can be depicted as a volume on x, y, and theta, in that space, that's where we're going to apply the tracking, as you can see here on the right. And why is that a good thing to do? Well, if you have crossings, then they are manifestly disentangled in the higher dimensional Lie group, and they can do tracking without having to suffer from taking the wrong exit, like we saw in the example of the catheter, where the doctor was navigating the catheter and the industrial tracker took the wrong exit. We won't suffer from that because there are no wrong exits, because we create a little bit more space in the domain of our images. By construction, the lifting layer, and this is what I called an orientation score, my PhD thesis in 2001. By construction, there are for orientation score transforms equivariance principles. So if I rotate and translate the image, then this will be a left action on the score. And if I rotate and translate the kernel, that gives me a right action on the score. And so I use a unitary group representation to rotate and translate my image. And by the unitarity of this group representation, you can deduce readily those two identities. Because since U is unitary, meaning UG star, UG inverse, from this property, you can deduce those two identities. And this is very important, because this hugely constrains on what I can do on these multi-orientation representations of these images. Because if I want to make sure that my image processing commutes with roto-translations, it commutes with UG, then the processing on the score must commute with LG. And since I fixed the kernel in my framework, I don't want right invariance, because I want to employ the directionality of my wavelet that I construct to make the score. So the operators on the scores must be left invariant, but must not be right invariant. That all follows from those two simple identities. So I need left invariant geometric control problems on the group and not right invariant in my specific framework where I first lift the image. Here I'm working with the group. So here, this is in this example, and I will do the group of roto-translations in 2D today. When I go to the group of roto-translations in 3D, then I have a homogeneous space, then I have SE3 quotient SO2. I'll come back to that, but for now, let us first focus just on the SE2 roto-translation group, where we have two translation parameters, one orientation parameter, and the space of positions and orientations is in that case one-to-one related to the roto-translation group. That takes me a position orientation to a position orientation. So talking about homogeneous space, or the group itself, there's no difference. So if I talk about the positions, space of positions and orientations, and the space of positions and rotations, in 2D that's fine, in 3D it gets a bit more complicated, but I'll come back to that. Now we're in the 2D setting, we have a 2D image, we lift the image to a multi-orientation representation, and then from the math, simply by the unitarity of the group representation, I roto-translate this wavelet, then by the unitarity of the group representation, you can deduce that the processing must be left invariant and not right invariant. And you can also deduce that you should not train the lifting layer, because whatever I train here could have well be trained over here. So there's no need to train lifting layers, even in a group convolutional network. Okay, let's go a little further. So equivariance. I want to make sure, if I rotate and translate this image of the apple, it's still an apple. So the processing on the image domain should commute with roto-translations in the image domain. So the group acting on the images, roto and translating the images. That means that I have to do left invariant processing on the orientation score. So whatever I do here has to commute with the left action. And then what we're going to do is we're going to lift this image to an invertible orientation score. And then once we go to the orientation score, we're going to train diffusions, dilations and erosions, geometric image processing in this space. And then we're going to train in such a way that we get the desired output. We're going to train for at a certain position there is a blood vessel present, like, or there's no blood vessel present. Okay. And we're going to learn, the training takes place of what we're going to do to these volumes on position orientation space. So the feature maps are no longer two-dimensional, they become three-dimensional. And the training of these processes on this lifted space of positions and orientations, we're going to train PDE-solvers. And they will have, by left invariance, very little coefficients. I'll come back to the sparse networks that we train on in the lifted space. Okay, so group convolutional networks, I think it was already presented at this congress several times, I'll be a bit brief. We can lift the image to the corresponding orientation score. We want to make sure that the operator commutes with the roto-translation operator U. That means it has to commute with the left action in the lifted space. And then the only linear group kernel operators on the group are group convolutions. I think you're all aware of that. The only linear operators, kernel operators that commute with the left actions are group convolutions. Yeah, so what you can do is, okay, instead of training the neural networks by doing training neural networks on R2, you can train them on position orientation space, and that has a lot of benefits, as also shown by Rick Beckers long ago in my group, but especially thanks to the works, excellent works of Max Welling and Taco Cohen on equivariant neural networks. This has become a very popular technique, equivariant group convolutional neural networks. But I don't like them. I worked on them myself. I even discussed with Stefan Malot on the scattering operators to include this group geometry in the equivariance principles. But I must admit that I don't like them. Why is that? It's still, we have kernels sampled on a grid, some weights. We're training some kernels and then some nonlinearities, some defined linear units. And then, yeah, okay, we get great results with them, but then when we have the network parameters, what really happened is not really traceable via PDEs or differential geometry. So I want to get rid of the rectifying linear units, so there will be special cases of morphological Hamilton-Jacobi PDE-solvers. And I want to get rid of kernels that are not parameterized or do not relate to a nice convection diffusion or convection erosion PDE. I don't want to train matrices, sampled kernels, the samples of the kernels, one by one, optimizing all these values. Now I want to train the shape parameters of the kernels. That's our Green's functions of PDEs. Okay. So what we do is we lift it. There is a theorem that we have, like you don't have to train the lifting layer because you can do the training in the second layer. So you just first lift the data invertible to the space of position and orientation space. Then you apply each time a transport, diffusion, and a dilation for max pulling and erosion for min pulling. Dilation is nothing else as doing max pulling over Riemannian balls. Erosion is nothing else as doing min pulling over Riemannian balls. So we're going to train the shapes over which we're going to do min and max pulling in the lifted space of positions and orientations. And we're going to translate that. That will be done by the convection methods. And a little bit of regularization with the diffusion, all on the group. Okay, so in each of these layers, the feature maps are now higher dimensional on position and orientation space. And then we have this PDE solver. We do a convection. Well, convection, that is just moving along the exponential curve in the Lie group, as we see here. And then we do a diffusion. That's a Brownian motion on the Lie group. And then we're going to do a dilation and erosion. That's max pulling and min pulling over Riemannian balls in the Lie group. And these shape parameters of the underlying metric tensor field that I put here on the blackboard, these will be the sparse, the few parameters that we're going to train in our network. That has a major advantage because of left invariance. You only have a few parameters that you need to train instead of all these kernels with all these pixel values that you're going to optimize. You're going to train the left invariant metric that underlies the diffusion and the dilation and the erosion. Yeah, diffusion is because it has to be left invariant diffusion. You all know what diffusion is on Rn. Replace the spatial generators dx, dy, replace them by the left invariant vector fields, and then you have left invariant diffusions. And they are solved with, because they're linear operators, they're solved with Green's functions. That was also an open problem that was raised by David Mumford. I computed these kernels exactly, but the core message of today is how do we get tangible, quick approximations? Because I did compute the kernels exactly, but they involved material functions, special functions, a little bit nasty to put in a GPU. So we need quick approximations of the diffusions and the dilations and erosions. That will be the main mathematical topic of today. Okay, before I go to the math, I want to give you a bit of inspiration from neurogeometry. It turns out that they did measurements on mammalians, then in the visual cortex, we have orientation selective cells, and we somehow create an orientation score in the back of our brain. These orientation selective cells, they encode per position multiple orientations, and then there are in neurogeometry some PDE models for how we connect local orientations. These are so-called association fields, and as pointed out by Jean Petitot, these association field lines, they can be modeled by sub-Riemannian geodesics, and sub-Riemannian geometry plays a role there. And yeah, then you can have PDE models for local association fields. So to just give the intuition of an association field, here we see on the right, we see a bunch of local lines. Then we identify these orientations. We lift them in the space of positions and orientations. And then we can project it back if we want. And that has the advantage that we can deal with crossings and bifurcations. And how do these association fields look like? Well, they relate to sub-Riemannian or Riemannian distance. A sub-Riemannian geometry is actually a limiting case of Riemannian geometry, where the weights tend to infinity. One of the weights tends to infinity. And these association fields, they are related to geodesics in the space of positions and orientations with respect to a left-invariant metric. The metric is left-invariant if and only if it has constant coefficients with respect to the left-invariant frame. I will only do the diagonal case because I don't want to adapt for curvature today, and also our experiments show that it is not very useful to do that, so I'll keep it just diagonal. I have a weight here, W1, which is, I'm in the orientation score, so suppose I'm a small car in the orientation score, I have a certain orientation, I can hit the gas, the cost for hitting the gas is W1, the cost for stepping aside is W2, cars can step aside, so that's in the sub-Riemannian geometry, infinite cost, W2 could be infinity, and W3 is turning the wheel. And then we see here, when this lifted car in this positions of orientations, then we look at all the possible endpoints, and then we get the sub-Riemannian or the Riemannian balls. So if I have a metric tensor field G, as I explained over here, expressed in the double left-invariant frame, then this is the distance, and these Riemannian balls, they nicely model the association fields from neurogeometry. And they are just parameterized with a few parameters, W1, W2, and W3. So instead of training sampled convolution kernels on a grid, these parameters directly. We have only 3 parameters instead of 7 times 7 times 7. Samples of a kernel that I'm training in a group convolution neural network. So the only thing that I'm going to train is convection for centering these association fields. And then I'm going to train the Riemannian balls over which I'm going to apply max and min pulling. And I'm going to train also with the linear units linear motion on position orientation. Then the only thing that I have to do, and that's a nice thing with mathematics, it reduces your model a lot. You only have to train 3 parameters instead of this very big convolution kernels. Okay. So here we have the association field, and here you see if you lift it to the position, space of positions and orientations, then you have geodesics and Riemannian balls and the shape parameters of these twisted rugby balls. That's what we're going to train. And that's essentially what a PDE-G-CNN does. Now, here we have the metric tensor field, the cost for moving forward, stepping aside, turning the wheel. And then we have these different shape parameters, and then we can do some diffusion and position orientation space. In a paper by David Mumford, there was the convection diffusion process and also the purely diffusive process. And I did derive the exact solutions of these kernels on SE2, also on SE3. But they involve special functions, and we need quick and tangible approximations because this has to be fed on the GPU. And I will give you today the tricks how to make these quick approximations. But here you can see these are the exact kernels. So this is what a diffusive process looks like. This is dilation. You dilate things. You do max pulling over Riemannian balls in the space of positions and orientations, because it's solved. And erosion is min pulling over Riemannian balls. And typically you use erosion to erode your lines, to make your lines sharper, dilations to extend. The thing is, and this is very important, diffusion is linear. Well, linear commutes with group convolutions, so the solution is going to be the convolution with the corresponding Green's function. And the shape parameter is only this W1, W2, W3. That's the only 3 parameters, and then I can train this diffusive process. But hey, dilation and erosion, that is nonlinear. Nonlinear PDE, right? No. Dilation and erosion is linear. It's just you have to adapt your notion what you mean with linear. If you say, I have a semi-field with multiplication and addition, then indeed, then this is linear and this is nonlinear. But if I replace the semi-field, where I replace the times by plus and the plus by min, then this is just an ordinary linear semi-field convolution. It's just over a different semi-field. So the implementations of this and this is essentially the same. You can do a parallel computing of the kernel. The whole algorithm is the same. It's just I replace times by plus and the integral by min. And then the Lax-Olenek solutions of these dilations and erosions, these are the viscosity solutions of the PDEs. These Lax-Olenek solutions are just given over here again by convolutions. Not linear convolutions, but semi-field linear convolutions. And rectifying linear units are no longer needed because they are covered in special cases in these morphological convolutions. We're going to get rid of all these bit of, in my opinion, ad hoc nonlinearities in the neural networks. We're going to just do transport, regularization, dilation, and erosion. And the only thing that we have to train are these left-event metric parameters. We can hugely reduce the network. Okay, so let's have a look here. Here we have an image. We first have to identify the local orientations in the image. Then we have the association fields, and then we complete the line. This is how you would recognize, if you look at this image, you will recognize, hey, there's indeed a line. These line elements are grouped to each other. And we have some association fields in our own visual brain that allows us to recognize, hey, let's extract a line from this sort of almost random set of orientations. But as I said, we're not going to do that. We're not going to do that in position space, but rather in the space of positions and orientations. So we're first going to identify the local orientations. We're going to lift them up in the space, positions, and orientations. Then we're going to train these association fields, these Riemannian balls, over which we're going to do max pulling and min pulling, solving the PDEs with just these coefficients that we have to train. And then that allows us to, at the end, extract. Okay, now a little bit more on the math. Okay, so I have, you know from convolutional neural networks, you have feature maps. And now my feature maps are not just on position space, but on position and orientation space. And I have to do, each time, a PDE solver. Convection for transport, moving particles around. If you do left-invariant transport, you do that with the right action, because the right action commutes with the left action. Each other. And convection is solved by a right action, and the proof of that is just moving along exponential curve. I'm going to train how I'm going to move along the exponential curve. I'm going to train how I'm going to do max and min pulling on the lifted space of positions and orientations. In other words, I'm going to train the association fields from neurogeometry. Where to center the association fields, that will be the convection vector C. How to extend the line, that will be the parameters for the dilation. And then the parameters for the erosion, how to sharpen the line. And the nice thing is, such PDEs in homogeneous spaces, they are solved with convolutions. And just like every linear kernel operator that commutes with the left action is a group convolution, every semi-field linear operator is given by a semi-field convolution, where you just replace the times by the plus and the integral by the min. And the shapes or the things in the network that we're going to train, there's a meta parameter alpha. I'll come back to that later. It's not so important. Set it to 1 if you like. What I'm going to train in the network is essentially only these weights of the metric tensor field. Now, some of you may say, yeah, but there's also a t there. Typically in our algorithms, when we do one step, we set t equal to 1. Why is that? The PDEs have homogeneity. They are semi-field linear and homogeneous in the generator. So if I replace t by 5 times t, that just means, you replace the weights by 5 times the weights. So the t is not so relevant. And it's just these shape parameters. Okay, the linear part, because there was some question. You asked, how do the linear convection diffusions? What does it mean on the group? Well, We all know that diffusion, if I have a random walker in the image domain in R2, and we just completely drunk, and then you count the amount of drunk man guys that end up at a tile, and you make a histogram, you get a nice Gaussian distribution. This is central limit theorem. The same can be done with drunk man drivers. Because an element in SE2 is just having a position and orientation. And if I do the stochastic process and repeat that in a limiting distribution, you get the forward Kolmogorov equation of the stochastic process, which is a convection diffusion PDE or a pure diffusion PDE on SE2. And I computed the exact solutions to these PDEs. Then you say, why don't you use these exact solutions in the algorithms? Well, yeah, it's exact, but expressed in terms of Mathieu functions, special functions, and every special function evaluation is secretly a numerical algorithm. We don't want special functions, we need cosine, sines, x and y. I need good approximations still of these analytic things. The nice thing is that I computed these kernels analytically so I could check all the numerical methods to the analytic solutions. So this is the drunk man's drive, where we have convection diffusion, like, okay, the guy has the foot on the gas and then randomly turning the wheel. That's the top, that's the manifold direction process. And then below, that's where even putting the car in reverse and etc. and randomly turning the wheel. And then you get these typical, and the shape, W1, W2, and the W3, it regulates the shapes of these kernels. Do not coincide with the Riemannian distance because there's a slight difference between the isocontours of a heat process and the Riemannian distance. Still, you can do Gaussian approximations of heat processes on the position orientation. Okay, so the exact solutions in SE2 for the convection diffusion I published that in the quarterly of applied mathematics in AMS, and but also recently in applied differential geometry, I computed for the SE3 case and the homogeneous space position orientations the exact analytic solutions of the sub-Riemann and the Riemannian heat kernels. Okay, but we need good approximations in practice because this has to be trained, this has to be fed to the GPU. And I don't want to work with Mathieu functions and difficult things there. So I need very simple approximation. Okay, so this was the linear neurons. You can center your neuron, that's done by convection, and then you can do some diffusion if you want, or some convection diffusion. But there's also nonlinear neurons, min and max pooling over Riemannian balls. You know, min and max pooling is done a lot in deep learning. So why not do it over Riemannian balls? And then we solve a Hamilton-Jacob-Bellman equation. And essentially, the Hamiltonian, the last event Hamiltonian, you can see that if you have the Fenchel transform, the relation between the Hamiltonian and Lagrangian, at essence, it boils down to the Hamiltonian and the Lagrangian in 1D. So you can show here, this is the Wickham solution for the Hamilton-Jacob-Bellman equation, that indeed, it's just a convolution with a kernel. So if you get control of the kernel, then you can implement this via a parallel algorithm because it's just a parallel semi-field convolution. Yeah, there's a parameter alpha. If alpha tends to 1, then you do a hard max pooling over a Riemannian ball. And if alpha is 2, then you have a soft max pooling over the Riemannian ball. This is known in mathematical morphology, where this is the structure element, and as I mentioned, doing mathematical morphology on higher dimensional Lie groups, at the end you can relate it to just 1D morphology on the distance map, on the sign distance, and then essentially what you see is that this is the process. You have a structure element put on it. Okay, so the geometric interpretation, that's important. So I have convection vector to center my association field in green. I have the association field for line extension, that is for dilation. In red, the association field for erosion. I'm going to train these association fields. Where do I have to center them? That's the convection vectors that I'm going to train. Where do I extend my lines, and where do I sharpen my lines? in order to get good feature maps. And this is nice, because typically you see that in the feature maps, when you project them down to the image domain again, you see locally how these association fields are reaching out to each other and say, hey, now we have enough communication, and now my filter is indeed in the feature map 1 on the line minus orthogonal next to the line, and then indeed I get a correct filter output when I apply it to a test image. I'm just training these association fields, and association fields, how they basically reach out for each other to say, hey, we're on the same line, that is visible in the feature maps of the network when we apply it to a test image. We get some geometric interpretation. This is important. For example, in an application I'm currently working on, automatic crack detection in bridges. We made a labeled data set for that with Rijkswaterstaat and ProRail. And then with these geometric learning algorithms, we can train these association fields, and then we say, hey, we found a crack over here, but it's because, hey, these local lines are connected, and these were the association fields that I trained by showing example images before, so that I justify that I find the corresponding crack at the end. And we have some applications on this. I was still integrating some of the geometric learning methods in this application. But, as I mentioned, these PDEs, they have analytic solutions. But the exact convection diffusions, wave functions, not so nice. It's cumbersome to train. Also, the Riemannian balls or the sub-Riemannian balls, I mean, I computed the Riemannian geodesics analytically, but before me, Yuri Sachkov did it even with the cursor case, everything. So, but still, these wavefronts are quite complicated to compute. So these Riemannian balls, in general, yeah, you can compute them, but it's very expensive. And to do a convection diffusion on position orientation space is very expensive. And I need something quick and practical. And I don't want to have any special functions. And for that, I do the logarithmic norm approximation of the true distance. So what happens in the logarithmic norm approximation? Well, you know, in left-defined problems on Lie groups, there is a difference between the Riemannian exponential and the Lie group exponential. These things are not the same. But if I take the logarithm of g, well, you get an element. And this is now not the Riemannian logarithm, but the Lie group logarithm. The Lie group logarithm, this is now an element of the Lie algebra. And you can just take the norm of this thing, and the norm is then by definition just at the unity element I plug in. And the logarithm, computing the logarithm on the Lie group SE2 or on the Lie group SO3, it's all very easy, simple formulas, some cosine, some sine, some x and y, no special functions. It's all very pleasant. And this is then nothing else as the square root of C1g squared times G11, the first weight, this was the first weight, G22 plus C3 squared G3. And recall, these things were the weights of the network, the W1, W2, W3 over there. And there are theorems in mathematics that say locally, well, if you move along an exponential curve or a geodesic, locally that's almost the same. You know, when you move a little further, it gets different because then the higher order errors kick in, and the second order variation of the connection, whether it's Cartan or Levi Civita, it will come up and perturbations will come in. But locally, it's quite okay. So initially, so I had some algorithms to compute the exact Riemannian distance, quite expensive algorithms. Then we had numerical algorithms, fast marching, and then we had PDE methods, and then we have GPU on the, still, it takes a few minutes to compute, or a few seconds, half a minute, to compute a full volume. It's too much. It has to be super fast. Then these, but you can approximate that by the log. This is something that you can compute very simple. It's almost like a Euclidean norm with some cosine and some sines in there. And the nice thing is that locally we have some theory. We did some error propagation. This is symmetric Riemannian manifold, so you only have to take care of the second order errors here, all the odd terms cancel out. And we studied a little bit on the coefficient of the error. So locally, they are good approximations, but when I plotted them and compared them to all the exact expensive volumes that I computed with the exact solutions, hey, it's not so bad. These logarithmic norm approximations are not so bad if the anisotropy is not too high. Because if the anisotropy gets very high, then the logarithmic norm approximations become very bad. Because the group is not commutative. And even though if I put my metric and let my metric collapse, and by putting the anisotropy higher and higher and higher, the Riemannian distance, because of the non-commutativity of the group, still has a thickness to the side. Whereas the Riemannian log norm, it collapses to a flat pancake. So then there is a nice trick that you can do. You take the minimum over the Riemannian log norm approximation and the so-called sub-Riemannian log norm approximation, which essentially, and I will skip the details here, it's a bit more subtle than this, but essentially it just says, well, this was the forbidden direction, let's put a 1 here, and then put the square root of g11 times g23 here. Of the filtration of Lie algebra, two-step group. That's why you put here 2 over 2 here. And the thing is, if you take the minimum of the two, you do the right thing. Because if it's very anisotropic, the logarithmic norm of the sub-Riemannian ball is actually a better approximation of the Riemannian ball than the logarithmic norm of the Riemannian ball. If you take the minimum of the two, you automatically take the right logarithmic norm approximation. You don't have to worry about jumping between the sub-Riemannian or the Riemannian norm approximation. You just take the minimum of the two. And then there's one more thing. This is all local. Very far out, everything is going to be Euclidean. And this was my PhD student Gijs who came up with the idea to take also the maximum with a kind of Euclidean length L. And then we compare this. Yeah, in German you would say zusammengebastelde quick analytic approximations, and we compare them to these exact solutions, and they're not that bad, they're quite close. It's good enough in practice. And moreover, we have local approximation theorems that tell you about the order. We can also analyze where the Riemannian approximation goes down the drain, and indeed, as you expect, when the anisotropy gets too high, it gets bad, because the coefficient, because of the d squared and then I must say I missed. No, it's correct. So in the second order term, sorry, there was a d squared. That should be after the alpha epsilon over 2 alpha minus 1. So locally we have good approximations. You can also see that, but also globally. It's interesting because the 8 fundamental reflections of the Lie algebra are both there in the exact Riemannian distance and in the logarithmic norm approximation. Because if I replace in the iconal PDE A1 by minus A1, nothing happens. If I replace in the logarithmic norm approximation C1 by minus C1, nothing happens. So all these approximations, that's why they're also globally quite okay, because they have the 8 fundamental reflection symmetries. Here you see and these reflection symmetries have everything to do with co-circularity, co-radiality, and co-angularity. So these reflection symmetries are also there in these approximations. And then shape-wise, they're not too bad. This is not such a bad approximation of that thing. The big difference is the thing on the left takes, even with an advanced PDE solver with the GPU, it takes, say, 30 seconds. Whereas the thing on the right is less than half a second, because it's just some cosine sine evaluations. I mean, that's super fast. So that's what we're going to do. We're not going to train these expensive things. We're going to train these cheap things. And that's what happens in the PDE-G-CNN. And this trick of approximating, this practical trick of approximating the Riemannian distance is not only useful for training the association fields in a PDE-G-CNN, it's also useful to use the association fields for connected component analysis in position orientation space. And we have a paper on that. And here I show some images, some example images, but I promised you we do a lot of projects in the semiconductor industry where we do automatic segmentation of chips, and we do most of the time just association fields and grouping the line elements, and then we automatically segment images of these. Okay. Another thing is optimal transport. In the optimal transport formulation, in the Wasserstein formulation, you have the Riemannian distance. But you can approximate this Riemannian distance now with something fast. And that allows you to do optimal transport not directly in the image space. So what's the problem with optimal transport in the image space? It leaks. When the optimal transport, they have a tendency to you don't stay on the contours. It leaks too much. But as an SE2, you can steer that anisotropy. You have the knowledge of the local orientations, and then you can send these particles for the optimal transport with the Riemannian metric in position orientation space. And then you go from one density to another density, and then you get a lot of benefits from that. And here I want to stress that in the Wasserstein formulation of for the optimal transport of going from one measure to another measure and then compute the barycentric interpolation as depicted over here, you just replace again this computationally expensive Riemannian distance with the quick logarithmic norm approximation. You know, where you took the minimum of the sub-Riemannian and the Riemannian logarithmic norm. And then you can, thanks to algorithm designed and invented by Gautam Pai, he took the synchrone algorithm on R2 and he adapted it with these new metrics that we had to quickly approximate the Riemannian distance on positions and orientations. And then we got with the synchrone algorithm a good algorithm to do optimal transport on position and orientation space. Now, why would you do optimal transport on position orientation space? Well, here you do barycentric interpolation. You see the problem with optimal transport on position space. It leaks to the side. Your particles don't stay on contours. I rather want to see how I have to deform this contour to this contour. So I can do anisotropic optimal transport, and then you get better shapes. And the nice thing is, and this shows also that this bit of zusammengebastelde approximation of the true Riemannian distance. Of course, we have local expansion theorems, new local expansion theorems. We have global symmetry results, but still it is a bit zusammengebasteld in the sense that, hey, I just take the minimum of the Riemannian and the sub-Riemannian distance. But it does do a good job, because you can see up there, I checked, because it's a general result, that optimal transport concentrate on geodesics. And here I took this optimal transport. I have one point over there. So I have to transport almost a point mass, but a little blurred, from one area to the other area. We do the optimal transport algorithm, and as you can see, the mass is perfectly following the exact sub-Riemannian geodesic that we computed. So we see that this zusammengebastelde approximation of Riemannian distance is not doing a bad job, because you can see, hey, indeed, it does follow, it does concentrate on the sub-Riemannian geodesic. Okay. A little bit of the questions that I will be a bit brief on this one. I say PDE-G-CNNs, I train group convolutional networks that are PDE-solvers. I said to you already, like, okay, they are still solved with convolutions over semi-fields, but then you would say, yeah, how did he come up with these PDEs? I have to say that I had the axioms of scale space theory in the back of the head. If you look at the axioms of scale space theory, or stable Levi, stochastic process and probability theory, and it's just a bunch of axioms. These axioms don't even use the word PDE, and then you can see, hey, you need a fractional power of the Laplacian for your linear stable Levi processes. So I just looked at these axioms of the scale space theory and I thought, what would happen if my field, if I would replace the field of multiplication and addition with the other semi-field associated to the PDEs, for example, the tropical geometry associated to the Hamilton-Jacobi-Bellman PDEs. And I just copied what I did before, and also what especially Powell's did before on the axioms of scale space theory, on generalizing the alpha stable Levi processes from a bunch of symmetry considerations. And I just replaced in that argument the field by the semi-field imposed by the PDEs. So then the nice thing is that if you come with a group and a semi-field that you want to have to be linear with, and I say, okay, that's the PDE you have to use. And guess what? The PDEs that I showed were the ones with the tropical geometry and the Lie group, and with the linear semi-field and the Lie group, then they come out. And so these PDEs are not just, you can derive them from axioms that actually make sense from a neural network perspective. I don't have to say to you that equivariance is important, but timescale equivariance is also important, because if I have an evolution, that's why I needed homogeneous generators in my PDEs. I mean, my stopping time should not matter. If I put t equal to 5, well, oh yeah, but don't worry, you will train 5 times as large coefficients. No problem. So timescale equivariance is very restrictive, because if you look at alpha stable Levi processes in probability theory, and when you look at the fractional power of the Laplacian, where alpha goes from 0 to 1, you can't go further than 1 because then the kernels get negative. And but that you end up with homogeneous power of the Laplacian for the alpha stable Levi processes for the central limit theorem on Rn. That is not a coincidence. That comes from this axiom. And you see, none of these axioms use the word PDE. Just symmetries for the network that I want. And all of these axioms have also been reported by applied papers on the design of neural networks, like these are desirable properties. And then the nice thing is, we have some properties. So in a GSI paper at the GSI Congress, we showed, hey, these PDE-G-CNNs, they have these properties like semi-field linear, strongly continuity, equivariance, timescale equivariance. But these properties force the PDEs. And that's a nice thing. And we managed to prove this on Rn. There are some difficulties on Lie groups, because if you work on SE2, the Fourier transform on SE2 is a bit complicated. The dual is R+, and you get some problems with the definition of timescale equivariance. I would be glad to discuss with someone one day, because I got far with it, but I haven't solved it on these. But on Rn, you can just show, okay, these PDEs are forced. And a very interesting tool in that is what I call the semi-field Fourier transform. The normal Fourier transform, you know, we already started in the presentations, decomposition into irreducible representations. And now I'm going to replace the times by the semi-field product and the sum by the semi-field summation. If I do that over the tropical semi-field, I get the Frenchel transform. Just use the Fourier transform to solve a linear diffusion PDE. The same technique can be applied to solve a Hamilton-Jacobi PDE with the Frenchel transform. And a great challenge that I would like to discuss also with mathematicians here in the room is, can we extend this semi-field Fourier transform to Lie groups? I have some ideas on this. That would be really great. Because with the semi-field Fourier transform, to derive that the PDEs are forced, these PDEs that I put on the whiteboard before, with the dilation, erosion, and the fractional diffusions, they were all alpha homogeneous. And it's just because of this transform. So if we can get a grip on the semi-field Fourier transform on Lie groups, then we can prove also that the axioms force the PDEs on the Lie group. But okay, we proved it on R2. We have a paper on that in the Journal of Mathematical Imaging and Vision, together with Gijs Bellard, a PhD student of mine. We put a lot of effort in carefully proving the result. Okay, so then all together. So we have an image. So we have the axioms, and then the axioms force the PDEs, and then these PDEs are semi-field linear, and they're solved by group convolution, and we just train the weights of this kernel, the weights of that kernel, and we train the convection. So we have now a lot of, and we don't going to use rectifying linear units, because, well, rectifying linear units are special cases of morphological convolutions and are non-optimal, so we completely remove them from the PDE-G-CNN implementation. We don't need them. And yeah, it works. And it works pretty good in the sense that if you have low regime networks up to 1 million parameters, we always see the same pattern here. Just look over here for the drive segmentation, vessel segmentation. A normal convolution of a network, 12 layers, 130,000 parameters. And with a group convolution of a network, you can get some advantages because you have group equivariance. In this application, because data already has a lot of orientations in there, you could argue, is the equivariance crucial for that application? Well, it does give you some benefits because you get better results with group convolution of networks with somewhat littler parameters. And then we do the PDE-G-CNN, where we only train the convection vectors, the weights for the dilation kernel, the weights for the erosion kernel. Much less parameters. We only have 3,600 parameters for the PDE-G-CNN and better results. So that is nice, and we applied it to many classification tasks, also digit classification, and yeah, we always see the same result here, a CNN with 40,000, and we just need 2,000 parameters. There is, of course, a catch here. What is the catch? The networks are parameterized with a very few parameters. But if you look at it from the practical point of view, these feature maps, when I apply it to a test image, is now on position orientation space. That means memory consumption times 8. You need 8 orientations, or maybe 16 if you use 16 orientations. 8 is usually enough, but that's also the problem with group convolution neural networks, which are, by the way, special cases of PDE-G-CNNs where I have multiple convection vectors that are just constrained around the center. People often think that a PDE-G-CNN is a specific thing of a group convolution neural network. No, no, no. The group convolution network is a specific non-optimal thing of the PDE-G-CNN. Because the convection vectors together, they will create the kernel that you trained locally. But the PDE-G-CNNs, they need little parameter because I just trained these shape parameters of the association field. They need much less. And you get better results. That is good. But the feature maps are high dimensional, so we have a memory problem. And that's what we're currently working on to work on sparse geometric learning. I think also in general with equivariant deep learning, I think a lot of effort has to be put now to sparsification. These methods perform well, but they consume a lot of memory. Yeah? Not on the complexity of the network, because that's low. You can analyze what's going on, but when you apply to a test image, all your feature maps are not a bit higher dimensional. So that's why in Eindhoven we collaborate also with the algebra group of 10 to shrink this and to make this more sparse. And there I also would like to refer to a beautiful technique that's now being developed in the UvA. From a computer science perspective, I really like this technique. It's called neural fields, and we're trying to combine now together with Erik to make a kind of sparse representations of these PDE-G-CNNs. But then we also get rid of the memory problem. Then we have only advantages. You have better performances, less network parameters, geometric interpretability, because we're training just association fields from neurogeometry. And now, if also the memory is tackled, then we're really happy. And that's what we're going to work on in the future. Nice thing with PDE-G-CNNs is it's very transferable. You train on the optical images, you test on X-ray images, and it still works with the PDE-G-CNN. It performs better than the group convolutional networks or the CNNs. Okay, because it makes sense, because you have geometric shape parameters. It's more stable to train the parameters of your metric tensor field than every pixel of every kernel in each layer. You need smooth variations. Of course, this can also backfire. And I once saw it in one of the applications of the geometric track detection in bridges. We did see, well, if you have really tons of data and the network complexity is going to up to 100 million or bigger, then geometric priors can backfire. Sometimes it is important, these high frequencies can improve the classification results. But in the low regimes, that's why geometric learning can really make a big difference compared to the normal convolutional networks. Yeah, but of course, if you have tons and tons and tons of data, at a certain point, what we see in applications, then if the network complexity goes far beyond 1 million, then the gain can also, will slowly start to backfire. If you have some expectations on how you propagate the line, sometimes, I don't know, you want to do a crack detection, but for example, that there is some paint nearby or some local structures, high frequency structures can be very decisive whether you find the crack, yes or no. So I must make a disclaimer here. These results are all good for geometric learning and PDE-based geometric learning in particular, in the low data regime, where you have networks like up to 100,000 parameters. Then it's all fine. Up to 1 million, it's all fine. Above that, I'm trying to get a grip on that, I see less gain. And even sometimes it will backfire. So I'm honest on that. Okay. So you see, here is a little bit why this is good. Of course, you can do more advanced networks, UNets, ResNets, and all kinds of techniques can be done. They can all be transferred to the PDE-G-CNN. Okay, but this is then for segmentation. After we do segmentation, we want to do tracking. We want to follow the blood vessels. For that, again, we use this left-of-hand frame, and then we have the metric. And it's very important that you use the right metric, because if you do geometric tracking directly on the image domain, we already saw these examples where you take the wrong exit at crossings or bifurcations. And then this was joint work with Eric Beckers long ago if you do the sub-Riemannian geometry, then you get good results, and you pass all the crossings. Still, in that framework, together with Jean-Marie Mirabeau, we made a kind of an asymmetric Finsler version of this, because it's sometimes very annoying that you can put the car in reverse. We have a plus control model of that. That's an asymmetric Finsler model. And then you can get rid of the cusps if you want. But, and then in these asymmetric Finslerian models, where you have one geometrical model, so one Finsler function here, for your optimization problem. And then in this optical image of the eye, we automatically find the seeds. Then if we have the seeds and the endpoints, we do one distance propagation and a backtracking, and the full vascular tree comes out. And we don't suffer from these typical problems from the crossings and bifurcations. Of course, there are still cases, a few cases where it goes wrong. For example, here, or when you have here a crossing and the bifurcation quite next to each other. But yeah, in the ophthalmology department in Maastricht, we're very happy with that, and we're currently applying that to practice full vascular tracking with one distance map on position and orientation space. Then it does not only involve these few weights, but then there's also a cost function that we develop. We could train it via PDE-G-CNN, or we do it with a crossing preserving vessels map. But then you can do one on propagation, backtracking, you project back on the image domain, and in one run, one distance map, one steepest descent back from all the endpoints, and then you connect every endpoint to the right corresponding initial point. That's useful for ophthalmology, where in ophthalmology they want to, for the diagnosis of diabetes, you want to analyze the vascular tree, and then image comes in, and then we can do automatic artery vein segmentation and geometric tracking. I will skip this. I just want to mention that in these geometric control problems on position orientation space, a lot of interesting things come to play. Two geodesics with the same length meet. If you do the viscosity solutions of the iconal PDE, then you only get unique solutions, so the non-optimal fronts are killed. But it's still very interesting to see where are these Maxwell sets, and they typically, in supremodern geometry, the Maxwell sets are even connected to the unity element, which is a local component of the Maxwell set, and then you can analyze this bit. You can do lots of theorems on that, on how that goes. Also, it's quite interesting to see that supremodern balls and supremodern geodesics, it is special because the cut locus, I mean, already next to the unity element you have the Maxwell sets, but in principle they are just normal limits of the anisotropic Riemannian set. Distances, distance maps converge. You take the highly anisotropic Riemannian and you take the limit g to infinity, then nothing happens. So it's all that is nice. And okay, so I just want to mention that there's some theoretical results also on 3D, but I'll skip that because I will come to the conclusion now. I just want to stress that everything that we showed here, we're now also working that on the space of position orientations in 3D, and together with Barbara, we're looking at these, how do we get good approximations for the Riemannian distance via the logarithmic norm approximations in 3D, and yeah, we found what is the correct section, and then we show that it's close to the distance the Riemannian distance minimizers over the fibers, etc. But that is something I will skip here. Here you see maybe on the right an exact supremodern geodesic that I computed, and now even if the end conditions are quite far, you still see that our approximations for the geodesics are reasonable, even if it's quite far out. And then I want to come to the conclusion. So we saw that we had a geometric AI algorithm with linear and nonlinear convolution. Nonlinear means semi-filled linear. If you replace the field of times and plus by the tropical semi-field. And yeah, these neural networks, they impact image analysis. PDE-based group convolutional neural networks perform a lot better than group convolutional neural networks. And they perform better than the convolutional neural networks. But, of course, there is the memory issue, and we should tackle that soon. And yeah, and one of the key aspects of that made it possible to implement the PDE-G-CNNs were these logarithmic norm approximations of the true Riemannian distances, because we are training Riemannian balls on position orientation space. Simple formulas and simple weights that we train. And for that, we applied this combined taking the minimum over the Riemannian log norm and the sub-Riemannian log norm, maximum with the Euclidean length. That was a trick that we applied, and that made it. And then there are, yeah, so for my PhD students and co-workers, also interesting papers. Also for people interested in optimal transport, I would latest paper of Gart and Pai, and yeah, and then. After the segmentation, we do also geometric tracking of an entire vascular tree in one run, one distance map, and then do backtracking. And, yeah, that concludes my talk. I think it has been proven for the Riemannian setting. Yeah, and for the sub-Riemannian, I don't know, but I cannot imagine that the result would not hold, because you can prove that the Riemannian subriemannian balls and the subriemannian geodesics are just limits of Riemannian geodesics where the anisotropy tends to infinity. Yeah, it's not that straightforward because there's because especially with the subriemannian geometry you have the Kurt locus nearby, and there's another thing with the subriemannian geometry that could be a thing that difficult. Subriemannian geodesics, you have them upstairs, you project them down, they can have cusps because sometimes it's better to put your car in reverse if you park it at the supermarket in the optimal path. It has cusps. We have models where we kill the cusps because we take the plus control model where we force the control to be positive or to not change its sign. But these are indeed issues that one has to be careful with the formal result by saying that optimal transport. I agree with you. You have to be careful by saying for the Riemannian setting it's known, but for the subriemannian setting things may happen. And the issue with the cusps is certainly a thing. If you just do the symmetric model, then I can see things happening there. But you saw numerically, it was fine. But that's not a formal proof. I would be glad to, if you have some ideas in this direction, I'd be glad to discuss a bit. Because there is also quite some interesting results on optimal transport on Lie groups also by Figalli on the Heisenberg group, where he shows in certain cases, he says, well, he had the subriemannian in the Heisenberg group case, and he showed in certain cases, yeah. Mm-hmm. Good. But I have to say that if your geodesic is cusp-free, then you can do the optimization downstairs. And then if you have the weights here, this is the W33, you can relate it to this, where you have G33 and here G11, and then the infimum over a curve, because this is theta dot s squared, this is the norm of x dot s with spatial arc length. So if I do the spatial arc length parameterization of the subriemannian geodesics, then it is indeed the square root of curvature plus 1. So I do penalize the curvature, but it's done upstairs in the space of positions and orientations. A change of curvature could be interesting. That would mean that we have to also do something with the second derivative of